Okay, good morning. I would first of all like to thank Huju and the other speakers for organizing this conference. And so here I'd like to just kind of give a brief outline of what I'm going to talk about in my talks. So I'm going to split the recordings into three sections. So the first one, that's where we are now, is going to be introduction to the topic. And so I will talk about the Plateau problem, the monotonicity formula for minimal surfaces, tangent codes for minimal surfaces. This part should be relatively elementary. And then I'll move on in the second recording and talk about the work of Hart-Simon on generic regularity for the Plateau problem. And I'll mention some generalizations and some new directions that you can go in that vein. And then finally, in the third talk, I will discuss new approaches to the work of Hart-Simon and sort of analogous statements for mean curvature flows. So I'll talk about how you can approach Hart-Simon without actually constructing the Hart-Simon foliation. And I'll also talk about an analogy between the regularity for the Plateau problem and mean curvature flow. And so this will come up only later and probably not even in this first talk, but everything. So what things I'll talk about today, when I talk about my own work, I'll talk about joint works with Yevgeny Lukamovich and Lucas Bolar, and also joint works with Kyungju Choi, Christos Mantelidis, and Felix Schulze. Okay. So to start out, I want to talk about the Plateau problem. Okay, and so the Plateau problem is as follows. So I want to consider a codimension 2 submanifold of Rn. And for simplicity, let me assume always that this is contained in the boundary of the unit ball in Rn plus 1. Although, of course, this is not strictly necessary. And so the Plateau problem asks to find sigma embedded surface sigma with least area among all surfaces. Least area among all surfaces. Sigma with boundary sigma equals gamma. Right. So you want to find the surface filling in gamma with the least area. And so this has a very long and rich history in the field of geometric analysis, but I'll just tell you the following somewhat surprising result, and that's the following. So sigma might be singular. Okay. So the first example, and sort of the classic example, is what's called the Simon's cone. The Simon's cone. Named for Jim Simons, who first wrote it down. Okay, and so the Simon's cone is a bit hard to visualize, but it's relatively simple. And so it's the set of points in R8 where if you write R8 as R4 cross R4, you want to look at points where the norm of X is equal to the norm of Y. Okay, and so, all right, we might depict this in the following way. Okay, so you might draw the following picture, but of course, this is in 8 dimensions, and so the picture is not completely accurate. For example, the complement of the Simon's cone has exactly 2 components, right? So that's going to be important for tomorrow, or in a moment. And so this is all well and good, but in general, cones except for Rn minus 1, which is a cone itself, but in a trivial way, cones in general will be singular at the origin. Right? So Okay, so it's not a smooth submanifold there. But on the other hand, C solves the Plateau problem. Okay, so what do I mean by that? Really what I mean is C intersect one has less area than any other sigma in B1, or even outside of B1, with boundary sigma is equal to the same as right. And so the cone has less area than any other competitor with the same boundary. Okay. So I think this is quite a surprising result, a surprising thing to say. And the proof is actually going to be very important, and was very influential for a lot of different directions one can go in geometric analysis. So I'm going to just briefly sketch the proof. So theorem. So this is proved by Paul. Okay, so this is just what I said above. The cone intersected the ball, solves the Plateau problem. Okay, so I'm going to give a sketch of the proof, and so sorry, and this should be all right. C U1 A plus. So we're going to decompose R8, the complement of the cone, into U plus and U minus, right? And so the part of the proof that I'm not going to describe is the following. Okay, it's the following statement. So using ODE methods, right? So by writing the minimal surface equation in a symmetric sense and analyzing the resulting ODE, it's not easy to do, but these people were pretty smart, so they were able to do it. You can prove that there exists plus or minus hypersurfaces that are O4 cross O4 invariant. So just like the cone, right? And so S plus or minus are in U plus or minus, and S plus or minus are minimal. Okay, so I'm sorry, shouldn't say and. So okay, we found these O4 cross O4 invariant hypersurfaces. They live in the both sides. They're minimal surfaces, and lambda S plus or minus lambda bigger than 0 foliates U plus or minus. Okay. So this, it's useful to keep in mind, this you could think of as being equivalent star-shaped. Okay, so you have these minimal surfaces, they're star-shaped, so when you dilate them, they foliate the space. If they weren't star-shaped, they would hit each other, hit themselves when you dilate them. And so you have a foliation of the complement of the cone by minimal surfaces. Okay, and so okay, now let me draw a picture proof of how you finish. Okay, So this is supposed to be C intersect the ball. Okay. And then suppose that there was some other competitor, sigma. And so if there was some competitor sigma which had less area than the cone, then we could actually solve the plateau problem and find sigma minimal surface with boundary sigma is the same as C intersect the boundary of the ball radius 1. Okay, so the actual proof, you don't quite need to do this, but this is a useful way of keeping in mind how to think about things. Okay. And so then what should you do? You take lambda times S plus, let's say sigma sticks out into the S plus side. Right? So you take lambda times S plus. If lambda is very big, this will be disjoint from sigma. And then you start moving it down. You decrease sigma until you touch. So this is some lambda naught S plus. And there's some contact between sigma and lambda naught S plus. But okay, the contact can't occur at the boundary. This can't occur here because the lambda naught sig plus lives in the complement of the cone. Right? So any positive scaling of S plus lives in the complement of the cone. And so therefore the contact must be an interior contact, but then using the maximum principle, so two codimension 1 minimal surfaces can't make tangential contact. Okay, so this gives you a contradiction. Okay, and so all right, so what have we learned here? Well, first of all, there exists in some dimensions singular solutions to the plateau problem. Okay, and so the analysis of singularities in the plateau problem is a very old subject, basically starting from this work and the work of Jim Simons, and even going back further. There's a lot of effort been made to understand these singularities better. And so let me just tell you the following theorem. Okay, and so I'll have some lecture notes posted, and so with the lecture notes you can get all of the correct references. But so I won't be completely accurate with all of my references. But this really is the work of combining work of Federer Fleming, DeGiorgi, Jim Simons, sort of that list of people with a few more names I'm probably missing. So. Okay, so consider a surface solving the plateau problem. And here I'm only talking about the codimension 1 theory. So higher codimension theory is very different. And as you've seen, right, we already have used the maximum principle here. And so minimal surfaces in higher codimension, they don't satisfy this sort of simple maximum principle in the way that we've been talking about. And so in general, the theory is much more complicated. The regularity is much worse. So today I'm only going to talk about things in codimension 1. And so the result I'd like to just point out is the following. So if you solve the plateau problem in Rn plus 1, then you have the following. Let's say it this way. Okay, so if we consider a solution to the plateau problem in the hypersurface case, right, And so when n is less than or equal to 6, so this corresponds to R7 and lower, then the solution will always be everywhere regular. Okay. And so when n equals 7, we've already seen, right, because above we've said that this cone, which is singular at a point in R8, so that's n equals 7, we've seen that this cone has a singularity and it solves the Plateau problem. And so indeed, this is in some sense the general situation of what could happen. And so you have isolated singularities for solutions to the Plateau problem. Okay, I'm not saying there's always isolated singularities. Actually, we'll see that many times there are not, but they can exist. And when n is at least 8, then things get kind of complicated. You can imagine, right? If you have a cone, you can take a cylinder over the cone. So you can take the product with R, and this will also solve the Plateau problem in an appropriate sense. And so you see now that an isolated singularity, if you go one more dimension up, becomes a line of singularities. And so in this dimension, the singular set becomes very complicated. And as you go on, the structure of the singular set is not very well understood. Recently, there's been some exciting progress on understanding this a bit better, but still, I would say that we don't understand this particularly well. Okay, so what I'd like to talk about is, so in my subsequent lectures, I want to talk about particularly the case n equals 7. And in order to do so, I'm going to need to use some sort of basic tools from the theory of minimal surfaces. And so what I'll say now is talk about the monotonicity formula. And tangent cones. Okay. Okay, so consider a minimal hypersurface in Rn+1, singular or not, doesn't really matter. Of course, when it's singular, you have to interpret what this means. And I'll just say that minimal means that it's a first order critical point for area. And equivalently, its mean curvature vector vanishes. Right? So in particular, area minimizing surfaces are minimal hypersurfaces. And so in this case, you consider the following quantity. Okay, so you consider the area of sigma in the ball of radius r, and you normalize it by the area of an n-dimensional disk in the ball of radius r. Okay, so notice that if you have, first observations, if you have sigma is equal to Rn, and you take a ball centered on the plane, then theta of sigma xr is 1. Okay. All right. So the basic facts about this object are as follows. Okay, and so R maps to theta is non-decreasing. Okay, so the as long you don't right. So if sigma has a boundary, you don't want to hit the boundary. But as long as you don't hit the boundary, then this area ratio is non-decreasing. Okay, and if okay, and so the other fact is that if the monotonicity ratio if the area ratio is constant between two radii, then the resulting surface is a cone in the annulus. Okay. And so this fact is very important in the analysis of minimal surfaces. And in particular, okay, so some consequences of this, right? Because it's a monotone function, we can take the limit as r goes to 0. So this limit will exist, and we can define it to be theta sigma at x. So this exists. Okay. And so furthermore, this is less obvious, but once you develop the weak theory a bit, you get the following. Okay, so if the function is monotone and then it decreases to its limit as you send r to 0, then you can see that it's basically almost constant at all sufficiently small scales. And so using the weak theory of minimal surfaces, you can rescale around a point to see that sigma is becoming, so this is supposed to be lambda j sigma minus x naught, is becoming conical in some weak sense. Okay, so you can zoom in around any point and pass through a subsequence and converge weakly to some cone. And we call these the tangent cones. Okay, and so if you're not an expert in this field, you may not know, but this cone may not be unique. And so it might depend on which subsequence you see. So at different scales, you could be seeing different tangent cone behavior. And in many cases, it has been proven to be unique, but in general, it's a big open question in the area, uniqueness of tangent cones. And uniqueness of the tangent cones is closely related to the regularity of the singular set. Although I'm not going to talk about that. Okay. So I'm going to use a fact a lot in my subsequent lectures, so I thought I would just give the quick proof. This is upper semi of density. Okay, so what I want to talk about is you often just say upper semicontinuity of density, and so lim. Okay, so what this says is that this density, and I forgot to give this the name. Okay, so the limit of the monotone quantities as you shrink smaller and smaller. And sorry, let me just pause for a second. And I should just say that when you take this tangent cone, the density of the cone, right, because the cone density doesn't depend on r, is going to be the density of sigma at the point x. Okay, so just so it's clear, the cone might depend on the sequence, but the density won't. Okay, so okay, back to this lemma, and so points with high density we're going to see are precisely going to be the singular points. So it's important to understand when points where the density is large. And so the basic fact about the density is that it's upper semi-continuous. And so this is very easy to remember if you think about the Simon's cone. And if you take a point xj, which is not at the origin, the cone is regular there. It's a nice, smooth, embedded surface. And so smooth embedded surfaces at very small scales look like planes. So, at xj, you have So at this point, you have density 1, because if you take a sufficiently small ball, the surface becomes approximately flat and the density limits to 1. However, so the density at the origin, well, you can convince yourself because the density at the origin is going to be bigger than 1. Oh, and I wrote 0. Okay, so what happens is sigma j limits into the origin and the density jumps up, but it can't jump down. Okay, so let me prove this because the proof is a nice warm up in using the monotonicity formula. Okay, so if we start at 0, then we grow the size of the ball, the monotone quantity goes up. Okay, so this will remind you sigma. Okay, and so if you ignore some technicalities, this limits to sigma. Okay, so you might be worried about some weird non-tangential behavior here, but it turns out to not be it's not a serious problem. And so then we can choose a subsequence so that this limits to lim sup theta sigma xj. So this is by pass to a subsequence. Okay, but still these inequalities hold. Okay, but now this is for all r, and we can send r to 0 again. So we find lim sup j goes to infinity theta of sigma xj. Well, the limit of this quantity as r goes to 0, we saw that the limit exists, and that's the density of sigma at x. Okay. So that's this theorem. Okay, and the second result, I'm not going to prove, is Allard's theorem. And so this is the epsilon regularity result in this setting. So. And so what this theorem says is that if you're minimal, and if the density is 1, then sigma is regular at x. Okay, and as usual, this result even holds with the density being 1 plus a little bit. Okay, but we don't need to worry about that. Okay, so moreover, so we have this point with density 1, and if you have a sequence of minimal surfaces which converge weakly in some sense, in the sense of measures, say, right? And in this case, the convergence is going to occur as smooth graphs near the origin, near this point x. Okay, and so again, you should imagine, well, you can always think about the Simon's cone. Okay. All right, so what you can imagine, you think about the Simon's cone, right here, the density equals 1. And we have these surfaces S plus on one side. And as you send lambda to 0, these surfaces get closer and closer to the Simon's cone. So in some sense, they are converging to the Simon's cone. The point is that Allard tells you that here, lambda s plus is graphical over the cone and converging. Okay, and smoothly converging. So the function defining the graph is smoothly converging. But no such property could be true here because the curvature, so the second fundamental form is blowing up. Okay. All right, so, and this is all compatible because remember that the density at the cone, well, it's equal to the density cone at the origin, and this is bigger than 1. Okay. So it wasn't obvious until now. It was, it's possible, though I said it out loud, that you had some cone with density less than 1, say, or equal to 1. But Allard's theorem tells you that because the cone is always, any non-flat cone is singular at the origin, it has to have density bigger than 1. Okay. And so finally, so the last thing I want to talk about in this lecture is what's called cone splitting. So you suppose you have a minimal cone, and that there exists a point x, which is not 0, such that the density of the cone at x is equal to the density of the cone. And I'll remind you that this is equal to theta of 0. Sorry. Okay, so for a cone, the density ratio is invariant as you scale the size. And so, but it's not clear, it's not true that if you center the cone at a different point, the density ratio is invariant. Again, for the Simon's cone, we've seen that if you center at a point not the origin, the density ratio starts at 1. Okay. And so let me just draw the picture. So here's the cone. Here's the point x. Okay. So we have that the density of the cone is less than equal to sorry. And by assumption, this is equal to the density of the cone at x. It's less than equal to, by monotonicity, okay. But now, so this is the ball radius r around x. The trick here is to observe that this entire picture would be the same if we dilated by r to the -1. So we're going to scale everything down by r to the -1. So I claim that this is equal to the cone intersect the ball of radius 1 at r -1 x over omega n. Okay, so in other words, if we just in other words, we're just going to scale everything down. The cone doesn't change. Well, we've scaled the volume by r to the -1, but that's compensated by canceling out to the r to the n of the denominator. Okay. And so now the point is that the new picture, we have okay. And so I should say we're going to send r to infinity. So this picture, we could have actually imagined it was like this, but that's kind of a bit harder to understand. And in the new picture, we have r inverse x. Then we have the ball of radius 1 at r inverse x. Okay. And as r goes to infinity, this ball converges to the ball of radius 1 at the origin. So again, this converges to the density of the cone in the ball of radius 1 at the origin. But this, of course, is the density of the cone. Well, it's the density of the cone at scale 1 at distance with r equals 1, but that's independent of r. Okay. So now, if you trace back through our steps, So we started with the density of the cone. We ended with the density of the cone. There was only one step in which we used a inequality, right? And that's this point. And so what you find out is that this must be equality for all R. Okay. So the only way that this could logically hold up with the monotonicity formula is that you have equality here for all R. But now this means that you have equality in the monotonicity formula. Right, between R equals 0 and infinity. Okay, so then this tells you that C is a cone. Well, it's already a cone around the origin, but also X, right? So if you were to move X to the origin, then you can dilate C and nothing changes. And so with some elementary geometry, you can see that this C splits a line in the X direction. Okay, so I'll stop here for this lecture. In the next lecture, I will talk a bit about generic regularity and the work of Hart-Simon.